Hey math kids, today we're going to talk about proof by contrapositive, or actually continue with this next part. But first we need to talk about modulus math, and so this triple equal sign thing is pronounced equivalent. So n is equivalent to 2 mod 3. What mod 3 means is if we divide by 3, the remainder would be 2 in this case. So it's saying if n is equivalent to 2 mod 3, then n is not a perfect square. So the contrapositive to that, if n is a perfect square, then n either has no remainder or has a remainder of 1 when we divide by 3. So that would be n is equivalent to 0 or 1 mod 3. Okay, so we have to test a couple cases. So if k is congruent to, or wait, sorry, I'm getting ahead of myself. Okay, so we're going to start with n is equal to k squared, where k is an integer. And if that's true, we have some cases. So if k is divisible by 3 is essentially what this is saying, then we know that k has to be equal to 3q, which is just another integer. Okay. If we do n is equal to k squared, we plug that in, so it's 3q, which would be 9q squared. We try to factor out a 3 to see if it's divisible by 3. And since we can factor out a 3, we know it's divisible by 3, and therefore we know it's congruent to 0 mod 3. Oh, I guess congruent. I was saying equivalent. Should be congruent. Okay, now we're going to test the next case. So if k is congruent to 1 mod 3, so what that means, once again, if we divide by 3, we have a remainder of 1. Then k in this case would be 3q, something divisible by 3 plus 1 remainder. And once again, q is an integer. Okay, so n is equal to k squared. So we plug that in, 3q plus 1 squared, which is going to give us 9q squared plus 3q plus 3q plus 1. And if we simplify that, and if we group these together, we can take out a 3. That would leave us with 3q squared plus 2q, and then plus 1. And so that's what we were looking for, something divisible by 3 with 1 as a remainder. And so that is the same thing as saying we're congruent to 1 mod 3. Alright, and we have to test the next case. If k is congruent to 2 mod 3, once again, if we divide by 3, we have a remainder of 2. So for that to be true, we just have to have 3q plus 2, so something divisible by 3, and then we add 2 to that. So n was equal to k squared, so we're going to plug this in, 3q plus 2 squared, which gives us 9q squared, plus 6q plus 6q plus 4, 9q squared plus 12q plus 4, and when we group these and pull out a 3, we're left with 3q squared plus 4q plus 4. So, what this is equivalent to, actually, I'm going to group that a little bit different to make it more obvious. I'm going to think of this 4 as 3 plus 1, and I'm going to group all of that and leave the 1 on the outside. Take out 3, we get 3q squared plus 4q plus 1, and then we have this plus 1 right here. So this is something divisible by 3 plus 1, which is actually 1 mod 3. So it didn't meet the criteria that we were looking for, but if you remember in the beginning, that's actually what we want. If n is a perfect square, then we should either get this or this. Oh, actually, yeah, it did get the criteria we wanted, because we got 1 mod 3, 1 mod 3, 0 mod 3. Those are the only outcomes when we plugged in a perfect square. And so since the contrapositive is true, we can now say that the original statement is true as well. If you need additional help, please come to Math Lab. Until then, calculator.